Welcome everybody to today's Simulation CFD Build Your Simulation IQ session. My name is Royce Abel. I'm one of the CFD experts here at Autodesk. And today I'm going to be talking about some of the finer points of meshing and Simulation CFD. This is actually based on an internal webinar that we had our meshing developer actually present to the technical team. And I wanted to make sure that we represented that to our customers. I thought it was a very interesting topic that he went through. One thing I want to point out to everybody is throughout the entire webinar, I encourage you to post questions inside of the questions window within the application. And I have Apollo and Caitlin and John all in the system right now to respond to those questions live. And at the end of the webinar, we'll pull out some of those more interesting ones that go into more detail during the live Q&A session. So this is actually our 13th webinar for the CFD series. In bold, I have some of the two more viewed webinars within YouTube. So if you're new to the series, I encourage you to start off with what's new in CFD 2015 and then go from there. And if you're looking towards what are the future topics, I encourage you to go to our forum post where we have all those listed. Right now there's actually none posted, but that will be updated very shortly. What's the news? This is when any of us really talk about anything beyond simulation. One thing I wanted to cover is that Autodesk Subscription Center will be end of life or taken offline this Friday, March 13th. For those of you that have always been frustrated with it, we'll be going towards what's called the Autodesk accounts. And one thing I just want to point out here is if you're looking to log cases online within the technical support team, this is actually where you would find that moving forward. So once you log in to accounts.autodesk.com, just go to the support section under the management, and that's where you can view and contact us and so forth. If you're stuck, you can follow this link once you download this webinar later, or the presentation, so that you can find some resources. And some other resources that you can actually find are some of our articles that we've written recently. I'm not really going to go into any of these in detail this week, but this is a list of all the written articles that we have done with links to them. So if any of them are interesting to you, I encourage you to jump in and read them. And if you're looking for some of our more commonly viewed troubleshooting articles, there's a link here as well that takes you to our kind of CFD troubleshooting landing site. So today's agenda. We're going to be talking about meshing. It's going to be a little bit more of an advanced topic than others that we've had. It's kind of going into some of the nitty-gritty of what's really going on when you pick certain options. And with that, I'm going to have just a couple poll questions to get people engaged. And the first one is I'm curious as to how many people have actually watched the previous Understanding Meshing Troubleshooting within Simulation CFD. I'll just give you guys about 30 seconds to respond to that poll. Finding right now that most people have not. I don't really think it would be considered a prerequisite. You can still get a lot out of this webinar, but I would encourage you to go back and watch that webinar if you do run into various error messages, for instance, when you're meshing. So we'll close that poll. And about 67% said no, they had not seen that webinar. And then lastly, I'm curious on everyone's experience with meshing. Do you just click on automatic sizing and run with it, or do you go all the way down to YouTube regions and surface refinement? You make all sorts of adjustments and really tune your model towards a mesh-independent solution. Great. This is actually a question I'm going to share with everybody. And you can see that for the most part, most users make some basic adjustments, and there's a good portion that use all their tools and regions. Probably one or two people that really consider themselves a meshing all-star, and hopefully learning some basic understanding here. Okay, great. Appreciate that. So when it comes to meshing inside of Simulation CFD, it's kind of broken into three parts. Of course, you have to start with your geometry, and you have all sorts of different meshing tools to create the distribution. And of course, lastly, there's the generation. So within the geometry side of things, of course, you need some sort of geometry that you'd create inside your CAD system. And then, of course, when you first launch that geometry into CFD, you're given the option to do some various geometry editing, from edge merging to small object removal, and then the next option there is defining what length scale you want to consider. Now, I'll go into more detail in some of those options. Those are the kind of three things that you'd consider once your geometry is inside a CFD. From there, in the sizing, of course, you can always go back to a manual meshing, but that's for the most part only leveraged for a motion model, or I use it a lot when I do 2D analyses. And then from there, you have your automatic sizing. And that's really where the bulk of the presentation is going to be around, really talking about what a 1D versus 2D and then 3D meshing and what that really means, and the outcome that you would see from that. There'll be a little bit of discussion on refinement regions and some different flags that would be leveraged for these different options. And then lastly, we'll talk about some adaptation. We're not really going to be talking about the actual mesh types that are outputted, but we will talk about how those are influenced by the options that we will pick. So within Simulation CFD, when you click on the automatic size button and make no other adjustments, what you're really doing is looking at all the edges within a model. You're looking at their lengths, the spatial distance between all the different geometry, and coming up with a distribution. So if you were to look at your model within outline mode, that's basically what the sizing algorithm is actually doing. Okay, so it's really a 1D meshing approach. But all the edges do communicate with each other to ensure that there's a smooth transition. So for instance, we look at these three images on the left, middle, and on right here on the screen. If you were to click on automatic sizing with this model, you would see the first image in that distribution. But let's make the assumption that we want it to add more mesh to this hole. And maybe there's flow going through each one of these holes, and we need to get a better pressure drop to calculate like a CV value, for instance. Maybe we click in those edges and the surfaces of those holes specifically. We would do a local refinement of adjusting the size adjustment to maybe like 0.5, and then we'd click on apply, and that would then take that setting and apply it to that selection. And then you could keep going and making other regional adjustments within your model. The last step to this is actually clicking on the Spread Changes button, and what this does is what's called a reconciliation operation, where it will actually influence the neighboring edges within the model so that the distribution is smooth. Otherwise, you'd see these very large growth rates going from one region to another. So those three operations are very basic, looking at the edges and coming up with your mesh distribution. Okay. So this is kind of some background of what is kind of going on as well. So if you're just to do a raw edge sizing and send that over to the mesher, okay, because that's what we're doing is within the UI, you're coming up with a distribution and where you want nodes to be located, and then sending that information to the meshing tool. And if you're just to do that, with us not doing some extra operations of how we configure the meshing tool, you would see this sort of mesh distribution going through this sort of simple cold plate. Okay, so of course, if you look at through the pipe, the mesh should be extremely coarse, and if anyone knows pipe flow, that's not nearly enough for that type of analysis. In reality, there's more than just the edge auto-sizing. There is some constraint logic to confirm that the mesh on a surface is more appropriate. So within the edge auto-sizing algorithm, there is a little bit more going on the back end. So this is just some background information that you never really hear talked about. So going from a 1D to 2D seems like the logical progression. So the next one is the surface AutoSizing. And at this point, it's all about surfaces. Okay. And in my opinion, this should be always considered for any model that you're doing. Okay. So after you click in the automatic adjustment and make any sort of size adjustments that you have, then you click on the surface and refine the checkbox is circled, and you click on refine. Okay. Now what this is doing is actually looking at the surface curvature, the surface distance or gap distance between parts, and the actual shape of this model. So in the end, we are then defining how large of an element we really want all around or upon all the surfaces in the model. And there's some other enhancements or but other benefits of doing this. For instance, when you have the surface refinement turned on, the thickness of the mesh enhancement will be more appropriate, because now a length scale of how we want the mesh to be defined at a given point on a surface is then used to define how thick that enhancement is going to be. If you take a step back to a 1D approach and look at how that's generated, the mesh enhancement is going to be driven off edges within the model, which then will propagate into a surface. You have a very large surface with a small edge on one end that's going to generate this very skinny surface in a model. And anyone that's seen like external flow around a building, and you see these extremely small mesh enhancement layers along the ground, that would be alleviated by turning on surface refinement. Okay. And this has a spatial reconciliation process as well, very similar workflow, where it will make sure any adjustments will spread across neighboring surfaces so that you do get reasonable distributions. I have the little cloud bubble by the gap refinement just because this isn't something you'd use always. This is more of a special case of when you really need to resolve mesh between gaps more appropriately. And we can talk about that more later. So here's a short case study of a valve. What you're seeing right here is basically flow going from down to up, where the top image is for edge AutoSizing and the bottom image is for surface AutoSizing. The key takeaway here is that if you look at the symmetry plane in the middle, where you do have some small edges, the edge AutoSizing routine does a really good job of getting reasonable amount of mesh in between that gap. But what it doesn't do is it doesn't resolve a tight enough mesh around the whole 180-degree sweep of this of the seating area between the poppet and the housing. So once you actually turn the surface refinement, you can see down here how the tighter mesh will actually go all the way around. You can see that on all the surfaces going around the sweep. Without this, you'd end up getting a very poor pressure drop, and you'd probably end up getting some influence on how the flow actually flows through this valve. So it's very important that you do use the surface refinement for these kind of problems. Okay? If you were to look at a kind of cross-sectional view through this poppet, you can actually see how in the left-hand image the mesh enhancement is extremely tight, as well as the distribution is extremely coarse. Once you turn on the surface refinement on the right-hand image, the distribution is very consistent across the perimeter, as well as if you look in that zoomed-in image, the mesh enhancement sizing, or the thickness, is more appropriate to the neighboring pets. Okay. Here's another view of what would happen. So in the image on the left, and this is for a mold cooling channels that would actually be leveraged inside a mold flow, but put into CFD. And if you look at the image on the left, this is really demonstrate what happens with the enhancement potentially. How on the bottom side it seems to be appropriate in terms of how the settings were adjusted and total thickness of the enhancement compared to the neighboring tetrahedrals. On the upper image, the enhancement overall seems much thinner than expected. And in the middle image, once you have the surface refinement turned on, you can see now how the mesh enhancement is much more consistent between the two images and the overall thickness of those layers compared to the neighboring elements. And now if we're making an adjustment to and reduce the thickness to get those elements closer to a wall, both the kind of inlet outlet of this cooling channel is much more consistent to what you would get. If you were to reduce the thickness of the layer factor on the image on the left, then let's say the top channel at this point is going to become extremely thin, but maybe the bottom one is now more appropriate. So you end up battling yourself and not really getting anywhere. So what are some very common customer issues or troubleshootings? These are the different conversations that we will have within product support. The first point is considering the minimum refinement length. So if anybody has dove into the diagnostics window and looked at the edge length section, they've potentially seen the minimum refinement length adjustment. And we've talked about this value before in previous webinars. And this can be critical. If this, we as a software will come up with a minimum refinement length. And there's some logic to how it comes to defining this. But potentially, if that value is too large for some smaller feature within your model that you care about, you potentially don't get enough mesh when you click in the automatic sizing. And then you're required to go in and make a lot of adjustments to get that mesh in there. If your minimum refinement length is smaller, you may actually get closer to the needed mesh in your model. Okay. The next option is kind of if you were to mesh your model, then potentially you could result in some error messages saying that the removed object is too small compared to the length scale or the mesh defined in a region. And pretty much what this means is that the small object removal, that physically deletes a surface or edge within a model. And if you have a coarse enough mesh, the mesher will actually basically smear over that region. And at that point, we'll build a mesh and cover that hole. Okay? And if your mesh scale in that region is smaller than that removed object, then it really can't smear that over anymore, and it can't really generate a mesh. So the small edge removal is a great tool. You use it a lot, but use it for extremely small features. If you're starting to delete features that are important or larger in scale that you don't want, it's much better to actually go into CAD and clean that feature up and then bring that back in. Where you'll see this affect you more often is when you start using that same geometry and then putting that through the adaptation. And maybe your initial adjustments were fine in terms of getting a mesh, but maybe after first or second adaptation, it's actually now in that region that you deleted, refined that mesh so much that now it's going to fail. Okay. So I just want to emphasize, the small edge removal is not required. It's sometimes really best left alone or used as a diagnostic tool to go back and repair your CAD. Now, for those users that leverage the gap refinement, or the GRL, or gap refinement length, as we'll sometimes refer to in emails, when you first define your model, you click on your automatic size, you make your adjustments, you click on surface and gap refinement. Your gap refinement length actually is initially the same as your minimum refinement length. Why is that? Because the software doesn't know proximity until you actually click on that refine button. Once you've done that, you can go into your advanced panel and then reduce your gap refinement to whatever gap refinement length you want. So if you want to get more mesh between pin fins, the distance between the fins, you then make that adjustment slider smaller than that distance. But then you actually need to go back and then re-click on the refine button to fully capture that adjustment that you made in the advanced panel. So really it requires 2 clicks of the refine button to capture an adjusted gap refinement length. Okay. And lastly, sometimes when you're doing all this gap refinement and actually go in and interrogate the mesh, it always seems like, not always, but sometimes you'll see that you'll get one less layer than you really defined. So you have a small channel, you define that you want 2 elements between the gap, and you only end up with 1. Then you increase it by, say, well, now I want 3, then you get 2. And that's because the way the gap refinement works, it doesn't take into account what will eventually be space captured by the mesh enhancement. And once you actually have that in there, that kind of cannibalizes some of that interior space, and the gap refinement and how it refines the neighboring surface mesh may not actually generate all the desired layers. So you see this increases the count by 1, and you probably at that point will get the desired outcome. So from 2D we go to 3D, and this is in the help and it's discussed. It's not really used much, but 3D of course would be volume AutoSizing. And within the software there's actually 2 different methods to affect how the interior or volume mesh is meshed, they're captured. There's the initial method that we created, which is just a checkbox within the advanced meshing controls, and this just defines a general growth rate within the model. So it's not really automatic sizing in the way that we normally talk about it in edge and surface, and it works reasonably well. Sometimes though it will add too much mesh in the model, and so that's why I normally don't use it initially. The second method is newer, and what you'll actually see when you turn this on within a flag is within the message window you'll see a line called volume AutoSizing. And this is actually going through the entire model and prescribing what size of an element we really want within the entire space. Otherwise, if you just had surface refinement turned on, we define the surfaces, but how the volume interior is created is not controlled by any sort of real logic beyond just let's fill in the space with mesh and let it do whatever it's going to do. Let's put it that way. In my mind, this isn't as robust as an approach. Many times when I do this with models, you'll see a warning of unresolvable variation. And all this really means is that it couldn't really fit within the logic or the functions that define volume AutoSizing. There's various reasons for this, but basically we'll just skip the volume AutoSizing and use whatever option you had previously. So most likely the surface refinement at that point. And it will tell you right under the volume AutoSizing in the message window that it was unresolvable. Okay. So in big bold letters, I wanted to capture this because this is a finer point of meshing within Simulation CFD, but generally is not needed, and it was added before we really did adaptation. So if you really need more mesh within the volume of the simulation, I would actually encourage you to run at least 1 or 2 adaptation cycles just to get more mesh within the interior where you actually need it. Okay? Because the volume AutoSizing doesn't know where the flow is actually going. It's just controlling more of the mesh on the interior so it doesn't get abnormally large. And anyone that's done architectural models have seen very, very large elements within an interior space due to the way that it just naturally grows. So here's just an example of a pin-fin heatsink. On the left is with surface refinement. On the right is with the method 2, the volume AutoSizing discussed earlier. And you can see how the mesh, as it grows away from the pin fins, grows very much quicker compared to how it's defined with the volume AutoSizing. And it goes beyond just the area around the heatsink itself. You can see in this area on the left-hand side how much larger these elements compared to how much more structured they are, in an unstructured mesh from end to end. Okay, so this is a better mesh to start with, but I wouldn't necessarily use it. I'd let the adaptation actually refine it as need be. So a few points on refinement regions. There was a group of people that replied to the survey that do use these, and refinement regions are great. Allow you to go into a model and tighten down zones that don't have an easily selectable part in that area. So in this image in the bottom, it's a very simple valve and a poppet, and we want to tighten down the mesh within that region. Okay. There's a few key points here just to think about. Once you add in these regions, if you have multiple regions added in, and let's say you go through process of clicking add, you place it where you want it to be, you click on get local size, and then keep repeating that without clicking the spread changes button, these regions don't really communicate. So if you had region 1, you tighten that down a lot and overlap that with region 2, then region 2 wouldn't see the adjustments you did in region 1. Now, if you were to add in region 1, make adjustments, click on spread changes, those spread changes do influence the result, the mesh distribution in the model. Now, if you add region 2, it would see the adjustments that you made and would influence the results. So if you didn't really understand what I'm saying there, what I'm trying to say is just, if you have multiple regions, go through the full cycle for each one so that they actually slightly or passively communicate to each other, but they don't directly. Now, if you go back and click on Automatic Size again within the window after you've done all these regions, you will pretty much knock these offline. They won't really influence the results anymore. You'll have to go back in and they'll still be there, but you'll need to redefine those settings again. So here are 3 images just showing very simply, as you click on the Get Local Mesh Size, you can see how it creates a new distribution along the edges of that region, but it doesn't influence the actual model itself until you actually click on the Spread Changes. And at this point, you can see the distribution throughout that entire model. So with mesh adaptation, to my knowledge, we take a pretty unique approach to how we do adaptation. For what I've seen within other products out in the market, what they'll mostly do is refine the mesh within the regions that it wants to change the length scale. Okay, so you'll be running your model and you'll see little zones within the model adapt. And initially we had implemented that same sort of approach, but we discovered, at least for our own tool, that doing that wasn't as robust. Okay, and what we have done is actually we do a full remeshing of the entire model based on the new length scales or new mesh sizing that we want from the model. Based on all the different error indicators that we use. Okay, so initially you set up your model, you mesh it, and when you do mesh it, use the same guidelines that you've been using for hopefully years. And at this point, allow it to solve to convergence, and the simulation will then finish. It will then adapt, remesh, and then those results will then be reinterpolated onto the old results will be interpolated onto the new mesh and cycle through again and again and again. Okay, so this is the preferred method when doing sensitivity studies, and of course identifies precisely where the model needs to be refined, and let it go from there. Okay. So here's a simple model of a valve, and what is going on here is, this is the initial solution, ran out for X number of iterations. Okay, and obviously this is not enough mesh to capture what is going on based on the later runs done with more iterations and with adaptation. So sometimes I will see users implement adaptation and they'll reduce the number of iterations very, very small, like 50 iterations, or maybe just keep it at the default 100 and let it adapt from there. And this is to show what would happen if you take this simple model and run it for 25 iterations, adapt, run it for 25, adapt, and do that for 3 adaptation cycles. And you can see from these 3 images, if you were to do that for 25 iterations, you really don't see the correct shear layers within the water and how that goes around the valve. It's not nearly as tight and captured, as well as kind of downstream here. It doesn't fully resolve that mesh. It doesn't go all the way to the backside of this valve. Okay, and as we move towards the right and we get more and more iterations, we even start seeing the features start to change as well. And this should make sense. If you run your simulation to convergence, you're going to get a more appropriate flow profile. So if you're going to adapt your simulation and capture those profiles, you want to make sure that you get the most appropriate results as possible. Okay. So the Mesh Adaptation Settings panel, if you notice, there is no option to turn on for heat transfer, but we do. if you're solving within the physics to solve for thermal, then we will adapt to the heat flux within the model. For the most part, running with 1 to 3 cycles will probably be enough for your model. And when you're doing sensitivity studies, that's probably your goal when doing this, then run with 3 or 2 initially with your model, save your cycles, and it's up to you to interrogate what is most interesting for you, whether it be temperatures on chips or flow through a pressure-driven simulation to make sure you get the appropriate amount of flow rate, or if you're looking at recirculation regions within a model to see that with an isosurface that section is being captured appropriately and not changing dramatically, then that's for you to interrogate and to decide. One thing I've noticed is that if you start off with too coarse of a mesh, eventually it will adapt and get to what you should be. But if you have a better guess of where it needs to go, a lot of times you can reduce the number of cycles to run down to 1 or 2. 3 is there because we have found over time that will get anything that you need for the most part. So that's why that's the default. Now they allow coarsening. I put a big don't use this option. And I'm not saying that you should never use this, but I've found that it's if you start with a good best guess that's a little on the coarse side, then you really don't need this. The adaptation will tighten up where it needs to be and just allow the mesh to stay where it started. Because allow coarsening isn't as an interesting algorithm as all the rest of the adaptation. Basically comes up and says, this region doesn't need to be refined. Let's allow that region to grow by X%. And sometimes that logic will result in a mesh that doesn't get generated through the cycle. That's why I decide, for the most part, to tell people not just to ignore it. Within the additional adaptation parameters, we have the full angularity, free shear layers. For the most part, I would use those 2 options in a model that I do. And all the rest are very much specific with a model that you might need. Shocks, you're not going to do that unless you're doing a compressible analysis that has shocks, for instance. In the advanced parameters, I pretty much leave those alone with the defaults. So at this point, if there's any questions that have come in, that'd be great. This presentation will be available at autodesk.box.com/CFD13. And so Apollo.
Yeah, there were no questions.
No questions at all? Wow.
Oh, we're getting a couple
Okay.
coming in now here. So why sometimes the approximate element count so different from reality?
Yeah, so one thing to take into account, that's actually an excellent question, is that the approximate element count is just that, but it only takes into account what is done on the edge meshing. So anything you've done within the surface or volume or refinement regions, for instance, none of that is taken into account. Sometimes I'm surprised how good it is, and other times it's horrendously off. So just remember, use it as a gauge of you make an adjustment and it gets drastically tighter. That's a good indicator that you probably went too far with that adjustment.
And then you want to talk about what transient features are with adaptation?
Transient features, it basically triples the number of cycles that you do, and will have a tendency to look at moving features within those 3 cycles. And if something is still a moving feature, an eddy, for instance, it won't adapt that region because it's not kind of fixed in space. For the most part, I think I've only used it a couple times. And generally, if you're running your simulation to convergence, then you shouldn't really have much of a transient feature. Okay.
How do we change the volume growth rate to get the results on the previous slide?
This slide?
I'm assuming so. So in this case, it wasn't a growth rate change. It was an adaptation run. Unless they were talking about this slide here. You maybe talk on the volume AutoSizing one, since that was probably it.
This one, you think?
Yeah.
Okay. So in terms of growth rate, remember this is method 2. So if we were to look at your setup, okay, this method by default has a growth rate of 135%, okay, which is the same growth rate as defined with that checkbox, but this is the one that actually defines how method 2 is controlled in terms of growth rate. So it's the same growth rate factor, 35 over the model. Does that address that question, Apollo?
Perhaps if there was more on that one, go ahead and feel free to ask further. But let's see. So did you show how to tighten the mesh of a particular element? No, we didn't cover talking on refining specific volumes. This was more on the background of how the AutoSizing works. For refining the mesh on a particular element, I would suggest checking out SimTV, where we have a video talking on basic meshing guidelines there. Let's see. When, why, and how should uniform mesh be used?
Uniform mesh, it all depends on your application. If you're to talk about electronics model, I like to uniform my heated chips, for instance. I uniform my distributed resistance. I uniform my fans and things of that nature. A lot of times I'll also go and uniform any surfaces for inlets and outlets to make sure that I have a nice tight mesh where the flow is coming in and out of the model. And that's where for electronics, if I'm doing natural convection analyses, I also like to do a uniform mesh within a refinement region where the plume is above the actual model if you're doing an external natural convection analyses.
Okay, let's see what else did anyone we missed. Someone said, I know you don't want to get into mesh types, but could you give some extra information on how to create extruded mesh?
Sure. So extruded mesh is limited in the sense that if we're to look at this model, I can extrude, for instance, this is a model, if people remember, of our first webinar that we did. This is that stadium. Okay? So you can extrude anything that has a consistent edge going along the extrude. Okay? So if I want to come in and extrude these ground planes, I'll come into Edit, Extrude. Actually, what I like to do is go to Outline Mode first, then go into Extrude Mesh, and then you'll see here an edge showing, or a line with seed points showing the direction of extrusion as well as where the layers will be located. And if I'm extruding this, what I really want it to do is go in the Y direction, okay, or up and down. So in that case, within the extrusion panel, I will change this until it goes in that direction. Go on side view now. Now we can see where that line actually is located. Now, you'll notice there isn't much of a distribution here. So if we turn off automatic, now I can define how many layers through that direction that I want, and also now define maybe a growth factor, or even if it was like a pipe flow and I want more layers towards the ends, I could even come in here and define some biasing towards the two ends. For the most part, extruded mesh is great if you're doing pipe flow. If you have many pipes in like a header distributor that are straight, great application for it. Otherwise, I tend to not use it much anymore. I used to use it a lot for chips, for instance, but at this point, the solvers and computers are so much faster that going through the setup of defining extruded mesh takes more time than just going through and clicking all those chips, for instance, and uniforming them, or compact thermal models, which is really just a two-layer extruded mesh in essence.
Just to add something to that, Royce.
Sure.
The question there was, he's a little bit more specific, so he was saying about using extruded meshes being clearances of the kind of external diameter of a spool valve. I think you kind of answered the question really, but just to add, we probably wouldn't use this in this application. What you could do is add an additional part in CAD where you could locally refine the mesh, and be really have really good control over it, or use a refinement region as we have done here.
Yeah, so if you were to think of this valve like I have in the picture right now, there's a few different options you could use to refine this gap. You can use the gap refinement and tell the software I want 4 elements in this gap, and then work pretty well. You could also go in and just tighten down these surfaces locally and keep refining them until you get enough mesh in that zone. You could use the refinement region to, in that zone, tighten everything down just like we did within these images. And then you could do like what John said and actually add in a few key volumes in this space. And this is the approach we used to use before we had CADed volumes, for instance, or our refinement regions. And this extra volume, you define it as the fluid, but it just gives you another part that you can then, for instance, uniform. This would be another case where you use the uniform option and really tighten down that region. Okay. I still use the CADed volumes often when trying to refine the mesh in between heatsink fins, for instance. There's a nice article on that. Or if I'm trying to get more mesh refinement for motion models, for instance, especially where there's really tight clearances.
That's it for questions so far, I think, Royce.
Okay. Let's give another minute here for people to chime in. One thing I wanted to show people is, if you remember that stadium model that we did, one thing I did here was I took that model and, with all the adjustments that I used initially with that, which I don't even remember if I had much to it, I had one volume adjustment done to the entire model. And then I took that model, which initially I had used surface refinement. I turned that off. So I looked at the 1D approach of what the mesh looked like. And then I also went in and turned on the volume AutoSizing with the flags and just looked at the mesh and what would it be with the summary image. So if we look at the stadium itself, this is the edge. You get a pretty decent mesh within the space itself. It's not so bad. But what we do see is, because of all the small clearances around the stadium itself, representing the floors and so forth, these layers are extremely thin all the way out into the interior space. And that really doesn't make a whole lot of sense. Okay. The aspect ratios are going to be astronomical, and it's really not good numerically. If we turn on the surface refinement, we see around the stadium it doesn't change all that much, but outside in the interior, we now do see that mesh enhancement is much more appropriate everywhere, and it doesn't really disappear like it does with the edge meshing AutoSizing. Okay, but what we do see here is that there is some general growth within the stadium itself that, with adaptation now get cleaned up, but I probably really wouldn't want that. I'd probably end up adding a refinement region in here and really tightening things down to get more of the wind profile through that stadium. So once I turn on volume meshing, then I get a much more consistent growth from the stadium detail all the way into interior space. It almost seems like if we were to look at the space around my pointer, like there's almost a refinement region there added in, and then it grows out into the interior space. So if we were to look at with and without volume in the larger domain, it doesn't change all that much, but right around the detail, it does a fair amount. Okay. And one thing that I learned from just this past week with looking at this is the error or the warning message saying the geometry really isn't acceptable for the volume AutoSizing. You can play around with this mesh volume AutoSizing error tolerance and increase this a little bit. And as this increases, you can potentially get around that warning message. So the default, I believe, is actually 12 for this value. I increased it to 30, and it did allow me to at least leverage the volume AutoSizing to some extent. What that error really is, I'm not exactly sure. I'd have to dig into that a little bit of what that would really mean. But it is interesting that you can capture, or you could leverage volume AutoSizing more if you wanted to by making that larger. And that's for any other questions, guys?
Nope, that's it.
Cool.
No, not at the moment.
Okay. Anything that you guys want to add?
I guess we could mention a manual kind of mesh refinement study, or like a mesh independent study. And so instead of using the mesh adaptation, which can sometimes take a long time, I don't know, I'll share how I do it and see if you agree.
Sure.
I mean, once I've got a good mesh on a model and I've got some results that I'm fairly happy with, generally what I would do is refine the mesh to like 0.7 everywhere, or maybe the fluid at least, and then see if the key results in critical areas change. And if they change by less than 5%, I'm fairly kind of confident that I'm mesh independent. If they change by more, then I'd probably think about refining the mesh further. This is a quick manual study. How does that sit with you?
Oh, that sits with me pretty well, but what about you, Paulo?
Yeah, kind of focusing on the critical areas, focusing on how those results change in those areas.
Yeah. And if you're using the Flex platform, which allows you to solve in the cloud, you could potentially do that mesh independent study very quickly. You could take this model, clone it 3 times, take your fluid volume, refine each one by extra 70%, or move it to 0.7, and run each one of those at the same time instead of waiting for the mesh adaptation to go through. At least it'll give you an idea if you're close enough, or maybe you're still changing a lot, you don't really know where to adjust it. That point would be a great time to then leverage adaptation. Okay. So with that said, there's 10 minutes to go. If there's no other questions that are coming in, then I will end the webinar. There was one just added in here that Apollo is applying to.
I was just about to type it up. But so the question just for everybody was, should we ignore mesh layer enhancement when using solid air as the fluid? So if you're using solid air, that is a solid. It is a material type equals solid. So by default, we will not be putting any enhancement layers in that volume since it is a solid. So we do leverage that for everybody that hasn't used it in small air gaps where you might just have a dominance of conduction. So if we think maybe some smaller electronics at times, we will replace those small air gaps with a solid material that has the properties of air, which we have one called solid air, and as a result, those regions will not have mesh enhancement in them since it is a solid.
There we go. Okay. With that said, I want to thank everybody for joining today's webinar. We'll have our next webinar will actually be on a Tuesday instead of a Wednesday in about 5 weeks' time. More information about that webinar will be announced at a later date. So again, thank everybody for joining, and have a great rest of your week.